How's everyone doing today? There we go. I am doing fine as well. Good to hear. All righty. Okay. Let's go ahead and get started. Oh, too much crap down here. Okay, so today we're going to look at chapter 14.5. Which covers the gradient of a function and the directional derivative. Okay. So suppose we have a function of two variables, f of x, y, and we start at some point AB. So we've seen that we can talk. We've defined a couple derivatives so far of our function. One of them is we keep y fixed and we change x by a little bit. Suppose we go and think about it as starting at AB and moving in the x direction, in the positive x direction, by a small amount, and seeing how our function changes. So as we take our limit as we move by smaller and smaller amounts, the rate of change, we can define the rate of change in that direction. Let me draw a bigger arrow, that's fine. So as we're moving in the positive x direction, right, in the direction of I, the vector, unit vector pointing in the positive direction, the rate of change of our function as we move in that direction was the derivative with respect to x, the partial derivative with respect to x. Right, we fix y, change x by a little bit, think of it as moving in the positive x direction, and then seeing how your function changes, taking a limit, etc. Okay, we did the same thing also by fixing x and moving in the positive y direction, so we're only changing y. Same thing, think of it as moving in the direction of j, in the positive y direction. And then looking at the rate of change as we move in that direction, as we just change y. And that is the partial of f with respect to y. So if you imagine like you're in a car, you're in a car and you're driving, and suppose the function f tells you the temperature at the point xy, right? So suppose you're at the point AB. So if you're driving, directly east, you can look at the rate of change of temperature as you drive, and that would be the partial of f with respect to x. And similarly, if you're driving directly north, you can look at the rate of change of temperature, and that would be the partial of f, well, with respect to distance at least, the partial of f with respect to y. But what if you're driving, say, like southeast or southwest, right? you're not driving directly east or directly north. How do we define the rate of change of temperature in that case? Well, that's the sort of thing we're going to want to do with several functions. And that involves, as we'll see later, the directional derivative. But before we get to that, we need to define the gradient first. I mean, what are we doing? Oh, we love it. Okay. So here's the definition of the gradient. So for a function of two variables, the gradient of f at the point AB is the following. So we usually write it as this upside down triangle. And we usually read this as, well, when we see this, we usually say gradient of f. But this guy here is del, this upside down triangle. And we'll run into the del. It's an operator on functions. And we'll run into it later again. But usually when we see upside down triangle f, we think gradient of f. So the gradient of f at the point AB. So at the function, you plug in a point AB, and it's going to spit out a vector. So the vector is simple. The first component is the partial of f with respect to x at AB, and the second is the partial with respect to y at the point AB. So you take the gradient of a function at a point. That is just a vector. First component's the partial of f of that function with respect to x at the point. The second component's the partial with respect to y at the point. And similarly, we can do the same for functions of 3 variables or more. For f of x, y, z, the gradient of f at the point ABC is, so if we have a function of 3 variables, right, we plug in a point in space, ABC, and it's the same thing, except now we have a partial with respect to z, and it's going to be a vector with 3 components. So partial with respect to x at ABC, partial with respect to y at ABC, oops, and partial with respect to z at ABC. Okay, so for functions of 2 variables, the gradient is a 2-dimensional vector. And for functions of 3 variables, the gradient is a 3-dimensional vector. But the gradient is just, each component is the partials, the respective partials at a given point. Okay. So the gradient assigns a vector to each point. So for example, if our function was, say, x squared plus y squared, function of two variables. So often, if we don't want to specify a specific point, we can just write gradient of f or gradient of f at a point x, y. Yes.
So this is a gradient, correct? This, like, it's like an upside down triangle.
Yeah, so we rate the whole thing as gradient of f, but the upside down triangle by itself, we just call del. You don't need to worry too much about it. Yeah, like for now, we're thinking of gradient of f as like a single thing. We're not thinking of del as its own thing, but we will use it by itself later, but I wouldn't worry too much about it. Yeah. But like that, the upside down triangle is like its own thing, and can be used in other contexts. But for now, just think of the whole thing as just gradient of f. Okay, so the gradient of this guy. So if I just plug in if I don't specify a point, it's just the partial of f with respect to x, and then the partial of f with respect to y. What is f sub x? Just 2x. And then similarly, f sub y is going to be 2y. And so if we want to see graphically what the gradient is doing here, you can pick a few points. And so let's really quickly, let me just pick a few points and then show you what's going on here. So at, for instance, 0, 0, our gradient is 2 times 0, which is 0, 2 times 0, which is 0. So the point 0, 0 assigns the 0 vector. Say at the point 1, 0, we get 2 times 1, 0. So 2x is 2, 2y is 0. 0, 1, we get 0, 2. Whoops, sorry, that's 0, 1. Negative 1, 0, we get negative 2, 0, 0, negative 1, and so on and so forth. We get 0, negative 2. And so when we plot these, so 0, 1. So if we look to the point 0, 1, 0, we assign the vector 2, 0. So start the vector there. The vector 2, 0 goes 2 in the positive x direction, 2 in the I direction, 0 in the j direction. At 0, 1, we get 0, 2. Sorry, that's supposed to be starting there. That's just not showing up that great. At 0, negative 1, we get the vector. Sorry, negative 1, 0, we get the vector negative 2, 0. At 0, negative 1, we get 0, negative 2. And then so on and so forth. So like at 1, 1, we get the vector 2, 2. Etc. And you can fill in more and more points. That's how the gradient works. To each point, it's assigning a vector. So graphically, you can start the given gradient vector at each of those points. And that would be how you would sketch the gradient. But we're not going to do that terribly often. And I don't want to dwell on that too much. Let's do another quick example of the gradient. So suppose our function is z e to the 2x plus 3y. let's calculate the gradient of f at the point 3, -2, 4. Okay. So let's first, before we plug in a point, just calculate the gradient of f for any x, y, z. So remember, it's a function of 3 variables. So it's the partial def with respect to x, partial def with respect to y, the partial def with respect to z. Okay, partial def with respect to x. Okay, so to calculate the partial with respect to x, we treat everything but x as a constant. So z is a constant and y is a constant. What happens when we take the derivative? What do we get?
You're basically just going to multiply this whole thing by 2.
Exactly. So it's a constant times e to the 2x plus a constant, right? E to the power something is when you take the derivative, you get e to the power something, and then you multiply by the derivative of what's up here. Well, 2x plus 3y, when we take the derivative with respect to x, the partial with respect to x, we just get 2. So we get 2z e to the 2x plus 3y. Similarly, taking the partial with respect to y, we treat everything but y as a constant. So z again is a constant. We have e to the something. So we get z e to the something. And then we multiply by the derivative of the power with respect to y, which is 3. And then what do we get when we take the partial with respect to z? Well, we're treating everything but z as a constant. So e to the 2x plus 3y is just a constant, right? So it's just z times a constant. And when we take the derivative, it just becomes the constant. E to the 2x plus 3y. My apologies for the terrible handwriting there. So when we plug in our point, x is 3, y is -2, z is 4. So for all of these, they're going to have e to the 2x plus 3y. So e to the 2 times -3, or sorry, e to the 2 times 3, which is 6, and then plus 3 times -2, which is -6, we get e to the 0. So for all the e terms, we get e to the 0, which is just 1. So for the first, we get 2 times z, which is 4. So we get 8 e to the 0, which is 8. For the second, we get 3 times 4, e to the 0, which is 12. And the third, we just get e to the 0, which is 1. Okay. Any questions about the gradient? Okay. So really quickly, we're going to show that the gradient works. It follows all the same rules as the derivative, as the normal derivative from 140 and 141. And so you can kind of use your intuition from those classes in calculating things. So suppose we have To functions, it's going to say functions of 3 variables, but it works just fine for functions of 2 variables as well. So if these guys are differentiable, don't worry too much about what that means. Everything in this class is going to be differentiable. And if C is some constant, then the following rules hold. So number one, if you take the gradient of the sum of 2 functions, it's the sum of the gradients, just like derivatives. So gradient f plus g is gradient f plus gradient g. Similarly, a gradient of a constant times a function, you can pull the constant out of the gradient. That's just constant times the gradient of the function. So number 3, we also have a product rule, and it works exactly like you would think. So the gradient of the function f times g is first times the derivative of the second, f times gradient g, plus the second times the derivative of the first, g times gradient f. So notice in this case, so f is just a function of 3 variables, right? So it's going to be a scalar function, and you're multiplying that by a vector.
So professor, with the gradient, do we like, since it's like right, the gradient f, we would take the derivative with respect to x comma y and z. Is that
right?
What
So you got a vector. The first component's f sub x, second's f sub y, the third is f sub z. Right. Was that the whole question?
Yeah. Thank you.
Okay. And then 4, we have a chain rule. So suppose we have a function of 1 variable. We'll write it as t. We'll do an example of this just to clarify. So the kind of things we're used to from 140 and 141. Sine of t, e to the power t, etc. Functions of 1 variable. So if we compose that with a function of 3 variables, so if you have like e to the power t, and if you replace t with a function of 3 variables, say x squared plus y squared plus z squared, so then you have e to the x squared plus y squared plus z squared. That's a composition of the 2. That's now a function of 3 variables, so we can take the gradient. And if we do that, so this is our chain rule for gradients. It works the same way. It's derivative of the outside function. And since that's a function of 1 variable, it's just f prime. So you take the derivative and then you plug in f of x, y, z. So right, so in our example, e to the x squared plus y squared plus z squared. So our outside function is like e to the t. The derivative of that is e to the t. And so f prime, and then plug in x squared plus y squared plus z squared in place of t. So then we multiply that by the derivative of the inside, which is our gradient of f, little f. So it's the same thing, derivative of the outside times derivative of the inside. And we'll do an example of this real quick. But these are all exactly the same rules. as derivatives from 140 and 141. So in many ways, we're going to think of the gradient as a way of taking a derivative of our function. Okay, so suppose g of x, y, z is going to be x squared plus y squared plus z squared to the power 8. So let's calculate the gradient of g. So you could do this by hand. Well, you could do this, just take partial g with respect to x, partial g with respect to y, the partial g with respect to z. Or we could do it like the chain rule way and think of it that way. We could think of this as a composition of two functions. So the outer function is the stuff inside to the power 8. So think of the outer function as being like t to the power 8. That's the stuff inside to the power 8. And the inner function, in place of t, for the inner function, we have x squared plus y squared plus z squared. So g we can think of as big F of little f of x, y, z. Okay, so from our chain rule, when we take the gradient of a composition, it's the derivative of the outside, and then instead of t, you plug in f of x, y, z, little f of x, y, z, times the gradient of the inside. Okay, so our outer function was t to the 8. What's the derivative of t to the 8? Right, 8t to the 7. Except we're replacing t. It's not f prime of t, it's f prime of little f of x, y, z. So we're replacing t with x squared plus y squared plus z squared. So 8 times x squared plus y squared plus z squared to the power 7. And then the gradient of f, so of little f, x squared plus y squared plus z squared. So the partial with respect to x is, of course, 2x. The partial with respect to y is 2y. And the partial with respect to z is 2z. So that's a perfectly fine way to write your answer. So what this is saying is, so think of this is like a constant function here. If you wanted to put this all as a single gradient, like as a single vector, you could bring that inside and multiply each component by that. But that's a lot more to write. So we can just leave it outside like this. Either one's fine. But that's how the chain rule works. No, you wouldn't have to do the chain rule in this case. You could just take the partial with respect to x, y, and z separately, but that's how the chain rule works. Okay. Any questions on that?
Can you go back for 1 second, please?
Sure. Like, yeah, okay. So if we want to put this as a single one. Sorry, go ahead.
I'm good.
Okay. So now that we've talked about the gradient, we can define the directional derivative. Okay. Okay, so for the definition of the directional derivative, this is important. We need to use a unit vector. And whenever we're doing directional derivative problems, you always need to remember there needs to be a unit vector that you need to find if there's not one given. So suppose u is some unit vector. So we're going to let u be a two-dimensional unit vector because we're going to define the directional derivative for functions of two variables. It's going to be almost the same thing for functions of three variables. It's going to be exactly the same thing, just one more variable. Okay, so we have a unit vector u. So the directional derivative, that is terrible. That's the directional derivative of a function f of xy, so a function of two variables, at a point a, b, in the direction of our unit vector u is, so we'll get the limit definition. So it's going to be the limit as t goes to 0. So it's going to be very similar to the partial derivative definition, except so it's going to be f of, so a plus t times h, which is the first component of our unit vector, b plus t times k, minus f of ab divided by t. Okay. So here's what's going on. So here's our point AB. And suppose this is our unit vector u. Right, so like this is, oops, u is hk. So it goes h in the x direction, k in the y direction. So we're multiplying that vector by t. So we get ab plus t times hk. So we get our a plus th, b plus tk. We're going in the u direction, except instead of a vector of length 1, we're going for a vector of length t. So we're looking at the point there, and we're looking at how the function is changing. So what's the value of the function if we go t units in the u direction? That's f of a plus th, b plus tk. And then we're looking at how that's changed from where we started at ab. So that's the change in f divided by the distance we've traveled, which is t. And then we're taking the limit as t goes to 0 in that case. And that's going to give us the rate of change as we go in the direction of u. So let me. So we can think of this as the rate of change of f when we're at the point AB and we travel in the direction of u. Our unit vector u. How's our function changing? Okay, so a couple things to notice. So from our definition, suppose we do the following. So suppose our u, our unit vector is I in the positive, the unit vector in the positive x direction. So, oh, sorry, I did not write, I did not tell you like how we write this. Let me do that here. So the notation for this is, so we do capital D, that's the derivative, in the direction of u, sub u, that gives us our direction, of the function f at the point AB. The directional derivative of f at AB in the direction of u. And u can be any unit vector. Okay, so for instance, if we take our unit vector to be I and the positive x direction, I've already mentioned that this is the partial with respect to x, but when we plug this into the definition, we see we get exactly the definition for the partial with respect to x. So that's the limit as t goes to 0, f of, so I is 1, 0. So it's going to be a plus t times 1, b plus t times 0, which is just b, minus f of ab divided by t. Replace t with h, and we get exactly what we wrote before as the partial of f with respect to x. And then similarly, the directional derivative in the direction of j, the positive y direction, of f at ab, we can do the same thing, and we see we just get the partial of f with respect to y. So the partial derivatives are specific examples of directional derivatives. Partial with respect to x is going in the positive x direction, in the direction of I. Partial with respect to y is going in the positive y direction, in the direction of j. Okay, but just with every other derivative we've ever encountered, we don't actually calculate them using limits, because limits are in general, kind of terrible to compute. So here's how we're actually going to compute directional derivatives. Okay, so once again, I want to emphasize this. So if you're given a unit vector, it needs to be a unit vector. So if U is a unit vector, then here's how we're going to compute the directional derivative. The directional derivative in the direction of U of a function f, and you can plug in a point if you want, but I'm not going to here, is just going to be the gradient of f dot the unit vector. Note that this definition works for functions of 2 variables or functions of 3 variables, or in fact, functions of as many variables as you like. For functions of 2 variables, the gradient of f is going to be a 2-dimensional vector. U is going to be a 2-dimensional unit vector. For functions of 3 variables, gradient of f is going to be a 3-dimensional vector. U is going to be a 3-dimensional unit vector. But very easy to compute. Just need the gradient of f, take the dot product with the unit vector. Okay, so for example, let me write this up here actually. For example, suppose we have our function is x e to the y. And let's give a directional vector, I'm going to call it v for a reason, and not u. Let's give a directional vector v 2, 3. So we want to calculate the directional derivative of f in the direction of v at the point 2, -1. Okay, so first thing you always want to do when calculating directional derivatives is notice in all the definitions of the directional derivative and how we compute them, we always have a unit vector. But if we're just specifying a direction we want to take a derivative in, we could give any vector we like. It doesn't have to be a unit vector. But in order to compute the directional derivative, you need to have a unit vector. Otherwise, you're not going to get the right answer. So what we need to do is we need to take the direction we're taking our derivative in and turn it into a unit vector. So that needs to be the first thing you always do when calculating directional derivatives. So we're going to take our direction v, which clearly not a unit vector. Magnitude is not 1. And divide it by its magnitude, so we get a unit vector. what's the magnitude of v? Careful. Yeah. You're on the right track. There you go. You need to square the components and then take the square root. So square root 2 squared plus 3 squared is square root 13. And so we'll just write that as a single vector. So we'll bring the 1 over root 13 in. So we get 2 over root 13, 3 over root 13. That's going to be our unit vector. Okay. So the gradient of f, without plugging in a point, so that's a partial of f with respect to x. I'll just write that out. Partial of f with respect to y. So the partial of f with respect to x, x e to the y, treating y as a constant, differentiating with respect to x is just e to the y. And the partial of f with respect to y is going to be x e to the y. Oops. So then plugging in our point, 2, -1, the gradient of f at 2, -1, plugging in 2 for x, -1 for y is going to be e to the -1, 2 e to the -1. Okay, so we need two things. We need our unit vector and we need our gradient at the point. And so we take the dot product. So the directional derivative of f in the direction of u, make sure it's a unit vector, at the point 2, -1 is going to be the gradient of f at 2, -1 dot our unit vector u. Well, the gradient of f at 2, -1 we said was e to the -1, 2 e to the -1. And our unit vector u was 2 over root 13, 3 over root 13. So take the dot product of two vectors, you just multiply the components together and add them up. So we get e to the -1 times 2 over root 13 plus 2e to the -1 times 3 over root 13. So we get 2e to the -1 over root 13 plus 6e to the -1 over root 13. So we get 8 e to the -1 over root 13. Okay, so careful. At the end, when you take a directional derivative, so when you take partial derivatives, those are a specific case of directional derivatives, but same thing. If you take directional derivatives, you're going to get a scalar, a number at the end, right? It's going to be a rate of change as you go in a given direction. And that needs to be a number, not a vector. So directional derivatives at the end, you're always going to get a number. So keep that in mind. If you get something other than a number, you did something wrong. But any questions about directional derivatives or this example? Okay, so tomorrow we'll have more to talk about with directional derivatives and the gradient. We'll finish up this chapter, but that's it for today. Have a great day, and I will see y'all tomorrow. Later, guys.
Thank you.
Thank you.